Last time we stopped at looking at family of cyclic trigonal curve and asking which were the correct statistics which gives a distribution for the number of points for the family of whole curve. So we could say for pieces of the genus we would get statistics. We could see also another way to get statistics from the work of Mélanie and also Mao Sheng Wang, which was looking at cube-free polynomial, which has the advantage of being the very natural statistic that you expect for the cube-free polynomial, but they didn't preserve the genus. So the question was, what are the statistics for the genus? So let me just recap that we're looking at this family of cyclic trigonal curve. And why do I write a cube-free polynomial like that? Because the genus is d1 plus d2 minus 2. Well, this is if d1 plus 2d2 is congruent to 0 by 3. And we look at the average number of points of that. And the first thing we did is we look at the average number of points of that on one component of the moduli space. And how did you look at the average number of points of that? Well, in this case, there's a very cute formula for the number of points. Well, basically, you get 3 points when you have a cube, you get 0 point when you don't have a cube, and you get 1 point when it's 0. So I got that the average number of points was given by the chi3 of f at the point A plus chi3 square f at the point A. And I have to put something like that. And this was also averaging over the family. I'm a bit corner here, sorry. So this was it goes like that. This was averaging over the family. So, okay, so if you average over the family, this amount to count square-free polynomial taking values. Square-free polynomial take every value which is not a 0 the same number of time. Everything cancel, and you get, so written like that, I just get that the average number of points is q plus 1, okay, by counting the polynomial taking value. But in fact, we showed more. So what we showed is, in fact, the distribution of the number of points. So we didn't just compute the average. We showed that the distribution of the number of points is the same as the distribution of the sum of those random variables. Where xi, so those random variables were taking value 0, 1, 3. So this was 1 over q plus 1. This is taking the value 0, and this is taking a value which is not a cube. This is taking a value which is a cube. So, whoops, sorry. I just wrote square-free polynomial. Okay, we're not looking at square-free polynomial. So this one is taking values which are, so this is taking value which are a cube, which happen a third of the time. And there's two ways to be not a cube, so this happens 2/3 of the time. But as we said, this is for d1, d2 goes to infinity. Okay? And the problem was that the moduli space, it's the union of those h, d1, d2, when the sum goes to infinity. Okay, plus the congruence condition. So in order to get statistics for the whole moduli space, I'm going to do a completely different approach, which is, so maybe I should acknowledge that this was work done by, so myself, so I'm going to write this. So myself, Ina Bukur, Brooke Feigen, and Mathilde Lalin. So in another work, which is in progress, but enough that I can tell you that we have results for the cubic extension. So again with, I forgot myself. Okay. But this time we joined force with Nathan Kaplan, which is here, and Ikin Osman, we just left. So another approach that we have is work directly with the zeta function. So, and this is not only following the work of Mélanie, but also inspired a lot by Mélanie. Following the work of Mélanie, we was able like that to count extension. So why is it the same thing? So first of all, why counting extension would be counting the number of points? This, we gave the formula last time. And I think, yeah, we gave the formula last time of that, just, using the fact that you can write the L function in two ways. And I don't want to repeat too much, but I think I wrote this thing. That if we were to average, and now this is over the whole genus. Why is it over the whole genus? Because my extension K are those FQ of C, and then I'm taking C, a cyclic trigonal curve of genus G. So there's no thing about D1 and D2. And why is it? Because in either the discriminant or the conductor, the primes, the F1 and the F2 will have the same power. In the conductor, it would be F1, F2, and the discriminant would be F1 square, F2 square. So there's no things of, that there's a different D1 and there's a different D2 and they have a different weight. So if I do that, the formula, let me just write, you take all the primes down. So you take the primes down in FQ of T, and what's important is their subsetting behavior. So of course, if you have a prime, you take primes of degree 1. So degree of P equal to 1. So P here, it's P ramifies. So for each ramifies prime, you get a point. This is the thing that the value is 0. Oh, I didn't write it like that. Let me use the notation I have on my sheet, which is going to be useful. I wrote it as counting the number of extension, which are cyclic of order 3, over K of genus G, which as this given prime here were ramified. And on the denominator was just counting the number of extension. And I need another term, so it's going to be a weird sum because this is a parenthesis. I'm very sorry. It's a weird Blackboard management. So there's the first sum. Why is it that ramified prime counts 1? Ramified primes, it means that the value of the polynomial is 0. So it counts for 1 point. And now I'm going to have the split prime. So primes of degree 1 again. And then I'm going to get this thing. And then, sorry, every split prime gives you 3 points. So every time the polynomial is a cube, you get 3 points on your. So you get that. Okay. So as I said, there's no work done here. It's just something that, well, the L function is, you can write it in 2 ways. You use the explicit formula, you do logarithmic derivative, and you get that. And now you average over the family, you flip the K sum and the P sum. So nothing has happened here, but now we have to compute those ratios. Okay? And this is exactly what Melanie explained. It's a cyclic extension. You can use class field theory to count those ratios. So count those ratios. So the ratio. And I'm just going to give you the answer. So if you count this ratio, and of course that's going to give you your probability. As soon as I write the answer, you're going to see which probability it fits. So for the split prime, you want to count this ratio as G goes to infinity. So maybe I won't say anything about the proof except it's following what Melanie explained, except this thing is that this is function field over FQ. So there are very nice different similarities. There's also very nice difference, which sometimes makes things more complicated and sometimes helps you. So one difference that I like very much is if you look at cubic extension over Q, so the prime and the conductor have to be congruent to 1 mod 3, of course, because I need to have a map from ZPZ to Z over 3Z, so you need P to be congruent to 1 mod 3. In the case of function field, you need that too, which is to say you need Q to be congruent to 1 mod 3. But the residual characteristic is the same for all primes. So all primes would show up in the conductor of cubic extension. There's no condition as being congruent to 1 mod 3. So one thing it will make, if you write the generating series, it will make it having double poles and not simple poles. Because you're going to do one over, you're summing over not half of the prime, but all the prime. But in fact, in a way, it does help you. Because the residue at the double pole will be bigger asymptotically than the residue at the simple pole. So there are different things which are more difficult, there are different things which help you. So if you count the ratio, well, what do you get? Of course, you get what you expect. For this one, you get 2 over Q plus 2. So you're in that, but you have a quotient of series, you apply the Dirichlet theorem, you take the pole, and you would get that. And for the other one, you would get, of course, oh, I hope I didn't put it, yeah. You get Q over 3, Q plus 2. Okay, so this shows that the average number of points is Q plus 1 over the whole class. Well, it shows more, but if you count the ratio, so if you want to know the distribution, you have to count the ratio E3K G, and now you have to set, your set of prime P would be all prime of degree 1, and then you would have a set of condition, okay? Where P would be the primes of degree 1. And E would be condition, well, inert, split, ramify, and they have to hold simultaneously. Okay, you're going to say, I want it to be inert at the same prime, split at the second prime, ramified at the third prime. So if you can count that, you can count the number of points. Well, you can have the distribution of the number of points. So here what we prove is that the mean of the number of points is the same as the mean of the random variable. Okay? Now by doing that, you're showing that the distribution of the number of points is the same as the distribution of the sum of the random variable. So we get the distribution. So you have the distribution for the whole space fits the random variable of each component. Even if you cannot prove that because you don't have the wrong limit. Also, what you have is that if you do the counting, so a very good sanity check, even if the error terms are too big, try to see if the main term fit, because they should. So if you count the number of elements on that space, it should be the sum of the number of elements on that space. And this will give for D1 plus D2 minus 2 is equal to G, and there'll be this congruence condition. And how do we know that? Well, we just computed that using class field theory. Okay? And how do we know that? Well, this is from the BDFL, if I might say. We computed those when D1, D2 go to infinity. Okay, don't use the error term is not good, but if you use the main term, it fits. So the number of elements on each component fits the number of elements of the genus that you compute here, which is, I think, for me, a very reassuring sanity check. Okay, so that's the story for that. And now let me move to trigonal curve, because I want to talk, so general trigonal curve. Well, you can say they're either non-Galois and they're all of them, because the Galois don't count for that much in that set. And again, this is a work of Mélanie that I'm going to talk about. We studied those one, so I'm going to do the same thing. So which is to say, for the trigonal curve, of course, there was no cute formula to write the number of points with the characters. But I can work directly with the L function, because the L function always gives me something. I do the explicit formula, and the L function relates the sum of the root to the coefficient of the L function. So I can do that. So what do I mean by that? I mean you take k over k cubic non-Galois. So what does it mean? It means that there's a curve that I will not write, but those are function field of a family of curve. And you look at the L function, so work directly. So the L function, well, let me divide by the Riemann zeta function, so I can write that this is PC of u. Okay? This is the usual thing, and this PC of u, it's j equal 1 to 2g, 1 minus u alpha jc. So I'm going to work directly with that. So on one, why would it give me something? Because here I have the alpha jc, so I have the number of points, because the number of points is related to the roots. And then I have, the coefficient of the zeta function, or the L function, and I'm going to be able to say something about it by doing the same thing, by looking at ramification in those fields. Okay, I don't know if I should take time to write the L function. Maybe I should. Okay. To give you an idea, so let me write. What I mean by writing explicitly the L function, okay, I'm using u as q to the minus s to save some writing. So what do? You write it in terms of the prime downstairs. I mean, we did it several times. So I write it in terms, and Mélanie did it also several times. I write it in terms of the prime of the downfield, which is fq of x, and I look at the splitting behavior. Okay, so let me use this notation. So if my primes downstairs split at 3 primes upstairs, I will have, and let me know if I write something stupid, but I would have that. So there are 3 primes upstairs, and they all have norm 1. So I can have that my prime downstairs stays inert, and then I would have 1 minus u to the 3 degree of p. So there's no minus because u is q to the minus s. Not that anybody objected, but I was kind of objecting myself. Okay, that's why there's no minus. Okay, and I can write all of them, huh? So, but here it's not a Galois extension, so I can have, so this is the prime downstairs. So I can also have things like, what can I have? I can have this 1, 1 square. Okay, I can write those, but I'm not going to do that. So there is 5 of them. 1, 2 I didn't name. So what's the last one? So 1, 2, I guess, completely ramified. Completely ramified, by the way, never does anything, huh? Because I get that. I get a 1. Okay? They're just those two that I didn't write, but you can write them. So you work directly with that, and you do the explicit formula. Okay? So again, the word explicit formula, if you're an analytic number theorist working over number field, is not an easy thing, but here it's very easy because the logarithmic derivative is very easy. So, and let me write them. I think those I want to write completely because I'm going to need them. So if I put my slides correctly, you're seeing what I'm doing. So I wrote the left-hand side in terms of u. I have the right-hand side. Now I'll take the logarithmic derivative on both sides of that. And you're going to end up with 2 power series in u and equate the coefficient. So this is the coefficient of q to the n over n. And on the right-hand side, if I do the coefficient of q to the n over n, well, I would get my prime in sk. Sorry, I didn't write sk. So in here, what I would have that the degree of p divides n. So when I do this explicit formula, I get u to the n. Here I would get your u to the degree of pn. That's how I get those conditions. And let me write what I get, 2 degree of p. Okay? And I would have a sum over all of those. I'll copy them from my sheet because I think I didn't write them in the same order. And this is for degree of p divides n over 2. I have 2 degree of p. And here I have summation. So this is the 1, 1 square. So degree of p. I have to write the condition because they're not always the same. You see, of course, this condition and this condition would give different count. And now for the prime, which are in S3, I would have 2 terms. So I have degree of p divides n over 3. And then I get 3 times the degree of p. And I would have minus degree of p. This is all simple manipulation. It's just that it's a case by case, so you have to treat every case. So what does it give me then? I can write the average number of point. Then the average number of point. So I can write the number of points. I'm taking n equal to 1. So I think I'll write directly the average number of point. I'll just flip my sum at the same time. So the average number of point. It's going to be doing the average of that. Notice that the n over 2 and the n over 3 will not show, because if I want the average number of point over fq, I need to take n equal to 1. Okay, there are no prime of degree 1/2 and there are no prime of degree 1/3. So I would just get 3 sum. So I'll get twice the summation. So I'm doing the average number of point over the whole space. And I don't know, maybe I'll call it, E3, give it a different notation. It's going to be all, so cubic extension. Okay. So before it was standing for something else, I'm sorry. Before it was standing for cyclic extension, now it's standing for non-cyclic extension. So if I do the average over this family, I would get, so I have the prime of degree 1. So degree of p is equal to 1. And for those, I get the 2 is the 2 that, the 2 is, there are too many 2's now. The 2 is the 2 of the degree. And then I have to count E3, K, G, P. And this one is for 1, 1, 1. Well, I guess I wrote it, huh? So what I wrote is an overkill. I wrote too many things. Sorry. And those I have to count on top. So let's say this blur is number. I have to put another one there. I'm doing something very simple is I take the formula which is there, I'm averaging, and I'm flipping the sum. So I go over all prime of degree 1, and for each of those prime of degree 1, I want to know the proportion of my extension, which at this prime have this splitting behavior. Okay? I'm doing now p ramifies in k, and I'm doing the opposite, k ramifies at p. I'm just flipping my sums. So I will get that one, and then I would get that one. Sorry, I'm doing the same thing again. I'm flipping my sum, so I don't need that. And for this one, I get a 1. So we have k, g, p, 1, 1 square. And finally, I will let another one, which I go over prime of degree 1. And this time, the splitting behavior is that they're inert. And this I write as 3. And you have to count those. So this will give you the average number of points. So how do you count those? Well, also Melanie explained that this is David-Heilbronn because I have a cyclic extension which is not Galois, except I'm over FQ of T. But this was done, so those were counted by, that's, T is close enough? And the T goes, no? HT, TH? Sorry, this is one of the problems I have in English. Is it HT or TH? HT, sorry. THT, sorry. So those were counted, and you just put the count there, and you would get the average number of points. And what it would give you, so one very interesting thing is it would give you that the average number of points is going to be Q plus 2 minus a small fraction, which is 1 over Q squared plus Q plus 1. So there's no contradiction with the random matrix model that you don't get Q plus 1 because the random matrix model is for the error of the number of points divided by square root of Q. So 1 divided by square root of Q, you don't see it. But it's in a way a family of curves which has more points than expected in a way. Because you would, if you have nothing else to say, you would say the average number of points is Q plus 1. But here the average number of points is not Q plus 1. Well, it's just the way those random variables do. And in fact, what you can get, so this is what Melanie proved, is that you don't only get the average number of points, since we also know the distribution by using the same thing. So if I look at the number of the ratio of my random variable are given by what? Well, the values of my random variable are 2, 1, 1, and the probability are those ratio. And now I should use the ratio. So I take all prime of degree 1, and I have a set of conditions. So I take all prime of degree 1, and I specify condition, and you need to know those. So this is very similar to what we did for the whole genus for cyclic trigonal curve. Let me see. Okay, so that's for the number of points when G goes to infinity. We saw the number of points when Q to the infinity. Then we saw that the number of points of curve over FQ is distributed as, well, it depends what point of view you take. So in family, so the number of points of C over FQ when C belongs to some families depending on the genus in Q. Well, it can be distributed at two things. So it's going to be distributed, well, it's not going to be the number of points, but it's going to be the error of the number of points. So it's going to be distributed as the trace of some matrix, so the trace of some matrix A in some matrix space. So as Q goes to infinity, and the matrix space can change. So for hyperelliptic curve, so this was USP 2G. So if you know the distribution of trace of matrices in USP 2G, you know everything you want to know about the distribution of the number of points, well, properly normalized by square root of Q. So also, if we take cyclic trigonal, so the group was, I didn't mention it, but the group is U2G. And if you take cubic trigonal, or cubic non-Galois, not too sure of it's also USP2G. So we didn't use it that much. It's a fact that it's like that. So soon I'm going to use it, and I'm going to use a different symmetry type to say something very nice about those family without taking Q goes to infinity. Because in fact, you can see the Q goes to infinity behavior, the fact that they belong to those groups, without taking Q goes to infinity. Okay, so, and now it's distributed as a sum of IID when G goes to infinity. Okay, we signed those three examples, and the IID are given with, well, different values and different probability. So what happened? What if Q and G go to infinity? So I have the Q, and I don't mean, so I could do two things. I could take what I have obtained for Q goes to infinity, take the G limit. I can take what I have obtained for G goes to infinity, take the Q limit, or I can just take both limit, okay? But of course, if I take both limit, which is what I want to do, it has to agree with those results. So if you do that, we can show that. So, and now I don't want the number of points, I want to normalize it properly. So Q to the minus 1/2 times the number of points minus Q minus 1 is a normal Gaussian as QG goes to infinity. By checking that all the moments agree with a Gaussian. So, and let me say in 2 seconds who is we. We is different people for each family. So by checking that all moment agrees with a Gaussian, okay, we know that the average is 0. We said it several times, the average number of points is Q plus 1. You're going to tell me in the family of trigonal curve, the average number of points was not Q plus 1. Well, I'm normalizing by Q to the minus 1/2. Huh? So the average number of points is Q plus 1. It doesn't tell you is 0, sorry, but it's more. It's a Gaussian. You know, the standard, the variance is 1, and you can show it's a Gaussian. So this is, you know, if you have a sum ID, this is what should happen. You know, it follows by the central limit theorem, and it's also follow in the matrix. You know, if you take the measure that you get on this matrix space, it should also be a Gaussian, though it's more difficult to show. It's a big theorem in random matrix theory. Okay, so what does it mean we can show or one can show? So this was done for the hyperelliptic curve. I want to give credit and also talk about what you need more to do that than to just compute the distribution of the number of points. So this is in the original paper of Kohlberg-Rudnick. So, and then what's the other family that I consider the cyclic trigonal curve? So this is in our paper. And what about for the non-Galois cubic? Okay. So in the paper of Ben-Ali, she noticed that if you want to know the average number of points or the distribution of the number of points, it suffices to know the density, which sometimes it is. But if you want to show that it's Gaussian, if you want to show things like that, you need error term. And the error term in those theorem, and the students which are in my group, we spend a lot of time talking about that, it's kind of not clear what is the status of those error term over function field. You know, there was, first of all, I think it was clear from Ben-Ali's talk that there was an enormous amount of work in the last year on that. There's a, very, very nice things which is done, but it's kind of not so clear at some point what is done over number field, what is transfer. So if you put an error term, which is very, very recent work, so using that, the fact that it's a Gaussian was showed by Frank, Thorne, and Maus. So the only difference between, of course it's a different proof, but the tools used are basically the same, but you can get to the distribution without error term, without knowing only the density, but to check that it's a Gaussian, to check that all the moments agree, you need an error term. So I think that's all I wanted to say about that. And now let's move to what about, okay, we look at the distribution for the number of points over FQ. What about taking those curves over FQ and looking at the distribution of the number of points over all the extension? So, which is all the higher moment. So this is very interesting because at the beginning I started to say well, the one level density is a very nice statistics because it picks the symmetry. Well, you notice that here I also kind of told you I was picking the symmetry, but at the Q limit, but without doing the Q limit, but by taking higher moment, I would be able to pick the symmetry for a limited support of the Fourier transform without taking the Q limit, and then I would be able to get the one level density for a limited support of the Fourier transform. So the point here is I'm not taking a Q limit. Of course, I know the one level density if I take the Q limit for unlimited support, but I want to have those analogs of those theorems over number field. So let's do that first for hyperelliptic curve. So what I want to know, let me call it traces of high power. And that's the last thing I want to say, and one level density. So what does it mean? I want to look at the number of points of C over FQ to the n, which is Q to the, so I'm going to write that as the summation J equal 1 to 2G alpha JC to the n. And I'm going to write that as Q to the n over 2 times the trace of this matrix. So it's convenient to work with the matrix. So I want to evaluate those for various n. Okay, for n fixed, I can always do that. But I want to evaluate that for n not fixed, which is to say, how big can I take n in respect to the genus of my family? So let's do that let's do hyperelliptic curve, as usual. And also, as usual, that would be due to Rudnick. So what's happening for hyperelliptic curve? Well, first of all, there's the random matrix theory that if I do the average of those trace, theta C of n, over the space of all hyperelliptic curve of genus G defined over FQ, and I take the Q limit, okay? So hyperelliptic curve is due to Rudnick. This is going to be for what I want to consider, sorry. So let me give a proper credit when I'm going to write that. It's due to Rudnick for Q fix. Sorry, for Q fix. And G goes to infinity, which I'm going to address on the next slide. This is what I want to talk about. But before, let me do a parenthesis and fix G. And let Q goes to infinity, and then it's due to Katz-Sarnak. So it's equidistribution theorem. In that direction. So everything you want to know about that, you know by USP. 2G, the trace of your matrix. Now you have to do the trace n. So again, I have this Q limit thing. So why am I telling that? So, okay, we know that we have that. And now we're going to do something which I find very nice, is I'm going to say, okay, what is that? What is integral of this? So this is now a theorem in random matrix theory. You can compute that. I'm not saying it's easy, but you can compute what is this average over the symplectic group. And this is going to give you, well, the nth moment, the first moment, yeah, when n equals 0 is 2G. I mean, this thing is clear. What are the other moments? I'm going to use this eta n, and this is for n is between 1 and 2G. And for n bigger than 2G, sorry, up to 2G. For n bigger than 2G, there's 0. And eta n is equal to 1 or 0. Okay. So what I'm saying here, okay, Katz-Sarnak equidistribution theorem is that. Okay? If I take a Q limit, I get distribution in a space of random matrices. There's no Q on the right-hand side. Q is gone. And now, okay, I can compute that. There's a group which is, it's a group of symplectic matrix. There's a Haar measure. Everything is known. If you work in that field, you can compute that the moments are there. So also maybe something I wanted to say that the Katz-Sarnak for genus is equal to 1. Genus is fixed here, huh? You get a group for any genus. That's actually due to Birch. It was the first evidence for the Sato-Tate conjecture in a very, very nice paper of Birch, and it follows from the trace formula. So that's another thing I wanted to say. So what's happening now, taking the other limit, so now fix Q and let G goes to infinity, and that's this work of Rudnick that I was alluding to. So for what do you get? Let me write the result with an error term, and then we'll see in which range it holds. So if you do the trace of those, so what does it mean? I'm taking those hyperelliptic curve, y squared equal f of x, I'm doing the trace of that, and I'm going over the whole space. Maybe, I think I wrote it like that. So what's happening here? If you compute that, well, you're going to get, oh, I think I should have put, yeah, okay, there's a minus which appear because, okay, in a number of points, it's minus the trace, huh? So I don't know, I mean, here there's a minus, I may have, yeah, here it doesn't matter because it's symmetric. So here it's going to give this minus because the number of points is minus the trace, I think. So under, I'm always confused by that. I'm sure I'm not the only one. The number of points is q plus 1 minus the trace. So if you look at, the number of points minus q plus 1, it's minus the trace. So I put a minus here, which, this minus here is correct if you count the correct thing on the right-hand side, which may be plus or minus that. Okay, so you're going to get exactly what you're supposed to get from the random matrix model. Let me write that. So this is Q fixed. Let me remind you, this is for Q fixed. So of course I'm going to write an error term. It cannot be true. But it's very interesting that you see the Q limit distribution for Q fixed. And then let me write the error term. So I'll just copy that from there to give you an idea of what it is. And then you have this sum. So this is not convergent, so you would evaluate it. And here you would see in this part, I have n q to the minus n over 2. And this is the only important part. Okay, and there's something else that I'm not writing. So this gives you the range in which this thing holds. Now the range, okay, you have to evaluate that too, but the range in which this thing holds is that, because this is a number. So this has to be small o of 1. So this tells you that you see the random matrix model in some range. So let me write that as a corollary. So for some range of n, so for n, and what is the range? It's below a log and between 2n. So yeah, my range that I have is between 3 log. Okay, if you work the error term, and here I'm going to get 2g, n over 2 minus 2g, so I get 4g. And I have minus a certain log. We have that this average, it's actually given by the random matrix model. So there's a certain range of n where you don't need to take a Q limit. This really fits the random matrix model. And what does it give you? I'm going to say corollary, but that's the same corollary. It tells you that the average number of points on the hyperelliptic curve over Q to the n. So, and the point is that C is over FQ. So my main point is my hyperelliptic curve are defined over FQ, and then I look at the average number of points. So here there's a normalization. So this average number of points is going to be Q to the n plus Q to the n over 2 plus small o of Q to the n over 2 when n even, and this is Q to the n plus, Q to the n plus small o of Q to the n over 2 for n. Okay? And this is, of course, for n in the correct range. So for n in the range of the corollary above. So this was first noticed, I think notice, it follows from the random matrix model, but that the random matrix model also holds for finite Q, and you get that. It was a paper of Brock and Granville, and the title of the paper was More Point Than Expected on Elliptic Curve Over Even Degree Extension. Okay? I think you can see why the title of the paper was that. But people, it was kind of surprising, and they didn't think that it would be, well, they didn't think. At first they didn't think, but in their paper they mentioned that you could see this Q, what happened is just you see this Q limit phenomenon for finite n, and it gives you that. So why also is it interesting? Because you can get, so I'm good. So I can go slowly because that's very nice. So if you look at all those powers, they determine a lot of statistics. If you get all powers of the trace for all n, it's like in a way like getting all moments. If you get all moments of a distribution, you know a lot of things about the distribution. So they determine a lot of statistics, and in particular, they determine the one-level density. And enough trace determine, what does it mean? It determines the one-level density. Of course, what it's going to amount to, I think you can guess, for support of the Fourier transform contained in some interval. And the interval delta can be computed very easily by which n can you take. So if you know all moments, you know the distribution. In particular, if you know all moments of the zero, you know the distribution of the low-lying zero, which is the one-level density. And if you know a couple of them, you know the one-level density. So you would get results which are exactly like the number field result. You would get result for the one-level density in limited support. And one interesting thing we'd see, do we get better limited support for that? Because after all, the family of hyperelliptic curve, this is the family of Dirichlet character over Q. It's exactly the same thing. So do we get better result for that? In fact, the answer is already on that slide whether you get a better result or not, because here you have n is up to 4n, and actually to get the bound you have to divide by 2g. So you would get exactly the same support, which I'm going to write in 2 seconds. So as a corollary of that, you get, if I take f to be a Schwartz function, and and I take the support of f to be contained in minus 2, 2, then I have that if I take the g limit, taking the g limit is perfectly normal. Huh? Over number field, we took the x limit. Taking the g limit is the same thing as taking the x limit. Okay, I'm not going to write to you the one level density, but we wrote it before. Okay, so this is the one level density. Okay, this is the sum of the zero. My function f drops super rapidly, so I get the low-lying zero. Well, at the beginning it doesn't matter because you have finitely many, but g goes to infinity, and also you normalize the zero such that the mean spacing is okay. So you will get that this limit will be the same as the g limit of, so that's a very nice way of showing the one level density of the one level density on the space of matrices. So how do I get that? This is Fourier analysis. This is very easy Fourier analysis because I have all the moments. So because I have all the moments, I can write my function in terms of the moments, and then I would get that. So you're going to show that the one level density is what you want by actually going to the one level density of the random matrices, because that's what I said. I just proved that all the moments agree. So by putting that into some Fourier analysis, if all the moments agree, you get that the one level density agree. And of course, this thing is that. If you want to write what is this thing, okay. So the theorem is the theorem is that. Actually, that's a corollary. We showed enough moment agree to have that the one level density agrees. And now that this thing is equal to that, well, I told you at the beginning, that's a theorem of random matrix theory. I can write, it brings nothing to write the density, just it's cute. Okay, it has unitary symmetry. So that's the one level density. So what I want to do to end is, okay, so we saw that we can compute statistics for the number of points for 3 families of curves. And then we saw, well, we can also compute high power of traces for families of curves. Oh, the one thing I wanted to say is I didn't tell you about Rudnick's proof. So Rudnick's proof is, of course, use the explicit formula. But before I use the explicit formula for kind of n equal 1 for the number of points, now I have to use them for all n and do some cancellation. So it's going to be more, I could say more about the proof, but I have the feeling that maybe some students are going to talk about that tomorrow. So maybe they will indicate, how the proof works. So you can do for a family of hyperelliptic curves, not only you can do the average number over FQ, you can do it over FQN in a range that is big enough that you see the random matrix theory, and you can do the one level density. Well, there's an obvious questions that one can ask. What about trigonal curve? So cyclic trigonal curve. And, I can say cubic non-Galois or cubic non-Galois. What about the 2 family that I told you the average number of points? So this one as we said, USP symmetry, U2G symmetry, sorry, and this one has USP2G symmetry. So if you compute all moments, we would see the symmetry. So for example, this one which already has maybe a weird number of points, but it would have a real bias over FQ squared. Okay? Not only the fact that the number of points is not exactly Q plus 1, and this one, you would have no bias because that's a family with UN. So can you compute those average of traces over the family? So can you compute the one level density for F belongs to some region? And as I said, so let me, it's here. Here for the support, I said that, but I didn't write that. For the family of hyperelliptic curve, you get exactly the same support that you get for the number field case. So if you can do that, you can also compare your support for the number field case. And now I didn't say that, but you can get the one level density, but you can also get the n level density. How do you get the n-level density? You compute the mixed moment. Which usually becomes a combinatorial nightmare, but you can do that. So if you compute the mixed moment, you will get the n-level density. And of course, it's going to be for support of f. I'm sorry, here I wrote, I'm going too fast. This is the support of the Fourier transform, and the interval will become tiny and tiny and tiny. Huh? Maybe I should not have used the n-level density. It's not for the n moment. N-level density, what I wrote here is the k-level density. If you do those mixed moments like that, you would get the k-level density, which we usually call the n-level density. Okay, so I think those are very interesting questions. To do that and see what you can do in those family and compare with the number field. And I have the feeling that people are going to talk about that tomorrow. Thank you.